And I want to thank Hexagon for this, for allowing us to use this fantastic facility and the great AV and everything else like that. So thanks to them. And again, let's be out of here by 8 o'clock or before, so we don't keep their staff any longer than they need to be here, since they're kind of volunteering their time. So I'm really pleased to introduce Christopher Smith, who works for Advanced Hydrocarbon Stratigraphy. I was going to say systems. He's been working for them since 2019. Most of his work, his analysis, he's done work on the Permian Basin, Anadarko and Arcoma basins in Oklahoma, and North Slope of Alaska, and the Marcellus Shale, is that right? Yeah, Marcellus Shale. He's been, since 2020, he's been expanding their unique technologies into non-traditional uses of not more than just hydrocarbon uses, and then I think he's going to talk about that some today, so that's great. And he'll give a sense of some of the variety of things that he's done. Prior to going to work at AHS, he got his PhD here in chemistry and biochemistry. That's what chemistry and biochemistry in the Department of Science. So in analytical chemistry, and focused on instrumentation, data analysis, programming, spectroscopy, electrophysiology, surfactants, and surface modification chemistry. So a lot of different things, his PhD. And prior to that, he got his master's and bachelor's degree from the University of Tulsa. So without any more yammering on my part, let me, Chris, have the microphone.
Phil, thank you very much. Cool. Hi, everyone. So I'm a pretty informal speaker. It's great that no one from the chemistry department has shown up, because they could all be horrified about how informal of a speaker I am. But they're not here tonight, so I don't need to worry about them. So we're going to go through, I know Arizona is very much a hard rock mining state. If anyone has a question where they're just like, hey, I really don't follow, why is this aspect important? Given that we've got a little bit more time than a lot of talks, go ahead, raise your hand, ask it. Happy to try to address it within reason. So we're going to talk about some work that we've been doing for the last 4 years across the border over in New Mexico, looking at the San Juan Basin and the Four Corners platform, really kind of looking at the stories that we can learn by analyzing subsurface volatile subsurface fluids that were entrained in old cuttings, fresh cuttings, old core, new core, and kind of what that taught us about the petroleum system in the area and what the implications were for carbon capture and storage in the area. So I want to start by thanking the U.S. Department of Energy and New Mexico Tech's Petroleum Research Recovery Center for their support and collaboration on this work. This work has been supported through a series of DOE grants. The first one that we had the opportunity to work on with New Mexico Tech was DEFE 0032064. I've been told I'm supposed to say the whole grant agreement number, which was for identifying faults in communication pathways that could serve as CO2 conduits in the San Juan Basin. That wasn't part of one of these CarbonSAFE grants, but that grant was written in direct support of a CarbonSAFE Phase 3 grant that New Mexico Tech had at the time. Beginning in 2024 and in 2025, we had the pleasure of working with them on another grant. This one was explicitly the CarbonSAFE Phase 3 grant, and this was their FE 0032242 Four Corners CarbonSAFE Phase 3 project. In terms of folks at New Mexico Tech, I really want to say thank you to William Ampoma, Cy Wang, Luke Martin, and Dana Ulmer-Scholl, who have all been great collaborators over there. So a little bit about who we are at AHS. We were founded in '94 by my boss, Mike Smith. You guys PhD in geology at University of Hawaii in '81. Worked at Amoco for 10 years. While he was there, if any of you have backgrounds in oil and gas, or you've worked for Schlumberger or interacted with Schlumberger in the recent past, you might know of a technology called fluid inclusion stratigraphy, FIS. So Mike developed this, patented this at Amoco. If you've come across Don Hall and Mike Sterner, Mike hired Don Hall at Amoco. If you have no idea who any of these people are, that's fine, don't worry about it. But so fluid inclusion stratigraphy was pretty important for Amoco. It's what the name suggests, you're going after the fluid inclusions in these rock samples, usually larger cuttings from tricone drill bits. And that was really helpful for what it was in the 80s and early 90s. So Mike leaves Amoco, founds AHS in 94, develops effectively Generation 2 technology, fluid inclusion volatiles. Again, the name suggests what it does. It's looking at fluid inclusions. This one solves a few of the quality of life issues that the Gen 1 technology had. The Gen 1 technology had potentially some significant issues with crosstalk between the samples. This one ran each sample individually, so that got rid of crosstalk issues, had some other capabilities. That technology is sold in 99 to ExxonMobil. They're continuing to use that as recently as 2018 at conference. They publicly stated that that's the first technology that new exploration wells go to. So Mike worked at ExxonMobil as an upstream research consultant. The reason I'm explaining all of this history, besides just who we are, is that that set us up for the advent of PDC drill bits. So PDC drill bits basically mean that your cuttings no longer actually look like rock. If you've seen them, you know, depending upon how aggressive the drill is, you're looking at either something that's pretty equivalent to talcum powder, or you're looking at pseudo rocks that have been recompacted, reforged on the sides of the cutters, and then they come up like that, and you have no idea if that's actually what the original rock looked like or not. So while he's at ExxonMobil, he's seeing this, he's seeing that any kind of rock that holds a fluid inclusion is going to be too traumatized, and he begins, after he leaves Exxon, developing our Generation 3 technology I'm going to talk about to you today, rock volatile stratigraphy. What we're doing here is, instead of going after fluid inclusions, because these really aren't viable anymore, and these didn't really tell you about the modern subsurface. They told you about what was happening at the time that that fluid inclusion was sealed, that it was kind of locked in time. We wanted to go after what were the residual volatiles still in pore spaces, still on fresh surfaces, and see if that could give us a more meaningful story about the subsurface, especially in places where the diagenetic environment wasn't appropriate for forming inclusions. And there are a number of places like that across North America. So what we have today is this Generation 3 technology, rock volatile stratigraphy. You're going to hear me call this RVS or RV Strat pretty interchangeably. I don't want to go through the technology in great detail, given that that's not the focus for tonight. What I will say is that we directly measure 40 plus different volatile compounds. You can see a breakdown of those here. So you can imagine with things like the C1 through C10 hydrocarbons, it's obviously going to be well suited for oil and gas, but there's a lot of other things that we're directly measuring, like water, carbon dioxide, these various sulfides, various organic acids and ketones, noble gases, even stimulation chemicals, and these are the actual fluids that we're extracting from those rock samples. We can do isomers and isotopes. We're not going to talk about any of that kind of data tonight. When we're doing this extraction, we pull it via gentle vacuum. So we're not using heat, we're not using solvents. If it's legacy, we will crush the sample while it is under vacuum. At the back end of the vacuum system, there's a liquid nitrogen cryo-trap that we concentrate all of this onto. And when we want to go ahead and actually measure this, what we do is, after that extraction is done, we just warm up the cryo-trap and things come off sequentially as a function of their sublimation point. We'll repeat this extraction twice on the same rock sample at increasingly higher vacuum conditions, and that gives us some idea of how easily things release, which we can relate back to rock properties, which we'll actually talk about a little bit tonight in terms of how readily CO2 lets go from rocks on the Four Corners platform versus in the San Juan Basin. But you know, this results in over 120 different direct measurements once you do all these different extractions under different conditions, once you look at things like ratioing them. And that gives you a pretty direct view of what is in the subsurface if you're looking at cuttings every 10-foot intervals, and really a good understanding of what is there and how is it distributed and how readily does it leave the rock. In terms of what we use for cuttings and the technology, so we use 0.4 cubic centimeters of rock for each sample. So if you take a look at the first digit of your pinky, it's about that much volume of rock is what the data I'm going to show you today comes from. We load them into these brass canisters. Here's a US quarter for scale. And then this has a polymer plug in the bottom, has this cute little nitrile septum on the top. That goes on to the instrumentation. The instrumentation shoves a syringe through there. If it's legacy, we crush the casing that this is in while it's under vacuum. And like I said, all that goes to a liquid nitrogen cryo-trap at the back end. And then once that trap is filled, once we warm it up, that passes to a mass spec. So we don't need a lot of rock. These can be very old samples. The oldest we've ever worked with commercially were 1930s samples from the Cook Inlet of Alaska. oldest we've ever worked with just because 1980s from Kansas. You get to cheat with older pieces of rock, older drilling technologies, because the surface area to volume ratio tends to be lower for some of these older types of drill cuttings where you actually got larger and larger pieces of rock, right? Whereas modern day PDC bit cuttings, very high surface area to volume ratio. All right, so I like to joke that we do some of the best subsurface science you've never heard of every day. So we're gonna have a little diversion here. We're not gonna talk about New Mexico. We're gonna go over to Louisiana, and we're gonna talk about what the end of the world looked like and how all the dinosaurs died, because I think this is a wonderful diversion before we get into actual science and things that matter in terms of CCS. So we will get to New Mexico, I promise. This is Louisiana, and there is a gentleman at University of Louisiana in Lafayette, Gary Kinsland, who has spent kind of the end of his career, he retired about a year or two ago, tracking down, borrowing, and stealing every bit of 3D seismic he can across Louisiana and East Texas. This is the KT boundary. Those are ripples. This is debris from Chicxulub. So these are the debris. This is debris as the Chicxulub tsunami came on shore. Not quite, but yes, these ripples are debris flows from Chicxulub impact. This is La Salle Parish. This is a core that captures one of these ripples. We have 30 feet of midway shale, we have 6 inches of airfall, and then we have several tens of feet of the mass transport debris, and then we have a pre-impact hard ground chalk. There's a lot of things that we measured. I showed you that massive list of 40 some odd compounds. There's even more that I didn't put on that list because we measure them, but they're not necessarily optimized or fit for purpose, but we still make these measurements. Here I'm showing you some data from that core, looking at 30 some odd samples that one of Gary's students had taken for his master's thesis. We got those core chips as an initial proof of concept study. And I'm showing you data for oxygen, CO2, sulfur dioxide, argon, nitrogen, helium, sulfate, and mechanical strength. And we get this from physically crushing the rock sample. Over here we have gamma ray. And the breakdown of this is the hard ground contact. You can tell that by the high gamma ray response. This section is the debris. And then here we have that 30 some odd feet of midway shale, and that represents time after impact, okay? And if you take a look at this, when we start down here in the hard ground, here's oxygen, and I think oxygen does a great job of telling the story. You know, we have a relatively consistent oxygen value. Now, there's a little bit of a bump here. In the third sample, sulfur dioxide goes off and then, you know, kind of comes and goes, but we don't see it prior to that. So this could be something like the Deccan traps in India going off, blackening the sky. Little pickup of CO2, little decrease in oxygen. But you get to the hard ground, and we don't know how long this is out of communication, how long there's no additional sedimentation. But we come up here to the debris, okay? And this is essentially our time zero. Impact has happened. You know, we're looking at, you know, what we're seeing either at the moment of impact or a few hours afterwards. And we can see that oxygen is going low, CO2 has picked up, notably sulfur dioxide is here. Now, it's not really a debris flow from the tsunami. This debris actually preceded the tsunami. I'm not a geomechanics or a geophysics expert, so I'm not going to get into that. Gary's got a great paper on this, although. But a few hours after the ripple was established, the tsunami would have come by and stirred it up. So you can see that there's this pretty clear break in the system, and so that's probably what this is. This is stirring things up as the tsunami comes by and stirs up the ripple. And then we come into the airfall. We've got our 6 inches of airfall, and this is where the story gets interesting for us. Oxygen falls away, CO2 starts going up, sulfur dioxide is just high, and there aren't opportunities to do geochronology on this shale, unfortunately, so you're left with kind of questionable depositional models to try to figure out how much time does this 30 some odd feet of shale represent. Gary's work would suggest this is about 200,000 years. So in that 200,000 years, oxygen is still falling. In the last 2 feet before we run out of core, CO2 finally rolls over towards a more baseline value. But take a look at that. Oxygen is still in collapse, and sulfur dioxide is still there darkening the skies. Meanwhile, argon and nitrogen don't really care at all what's going on here. And so this is, so we know that the rest of the environment, or at least the other gases in the atmosphere, aren't responding the same way that oxygen and CO2 are. So this is a really kind of exciting story, and this is kind of the fun science stuff that we get to do when we have time and bandwidth, and we're not desperately trying to stay alive as a small business.
Just a question.
Yeah.
So that's meters or
That-
feet?
What?
Is it meters or feet?
Feet.
Feet. So we got 40 feet of tsunami deposit.
Yep. And this isn't even the top of the ripple. This is on the side of the ripple. So the way they ended up getting this is the oil company actually targets the ripples as their reservoir. And the story behind this is that the company man, well, the well site geo goes out there, asks, why haven't we set the core barrel yet? Because they don't know that they're landing on top of the ripples. That had just been an accident. The answer is like, well, we haven't hit the chalk yet. And he says, set the damn barrel because I don't want to miss the chalk. So they set the barrel, 30 some odd feet early, and that's why we actually get to have this section, the 6 inches of airfall and all of this. But normally, the top of the ripple would probably be tens of feet higher than this. We're on the side of the ripple in this case. Yeah, yes, there is. I'm not showing that here, but yeah, that's in the master student's data. Okay, so this is just a track of the oxygen versus the CO2. I think it makes the story a little more easy to digest. Here's our pre-impact chalk. You can see where we divot out a little bit. CO2 kind of comes up. Here is our time 0 hours afterwards. And then here is our 30 some odd feet of shale on the day after tomorrow, where CO2 is just through the roof. We recover. Oxygen never really recovers, right? So it's an exciting set of data. This is the kind of work that we get to do when we have the opportunity to chase science projects like this. We're actually going to come back. We resampled this core a couple years ago at 1 foot intervals at the Texas BEG. We're going to flush the canisters that we use with Krypton prior to the analysis so no one can argue that we're measuring ambient air or other artifacts. We really look forward to finally getting this study out. But we're running a business, so how do we make money with this kind of data besides really interesting discussion pieces about how the dinosaurs died? So what do we make money on? So we use this kind of data to answer a lot of oil and gas applications, a number of CCS site assessment questions, and more recently, helium and hydrogen exploration and system analysis. So in the Four Corners area, we've worked on oil and gas, CCS, helium, and geothermal projects in places like Colorado, New Mexico, and Utah. Just talking about the released projects, these are things like helium exploration wells for companies like Four Corners Helium, the 5832 well over at Forge in Utah. And then what we're talking about today are looking at fresh and legacy cuttings and core from multiple wells in the Four Corners platform in the San Juan Basin for New Mexico Tech in support of their DOE CarbonSAFE projects. So kind of finally doing what I should have and getting into the science and explaining the study area and the problem. So what we're looking at today is kind of an offshoot story of what we've put together doing all this work for New Mexico Tech. A lot of it might speak to things that matter for CarbonSAFE. A lot of it just speaks to interesting things about how the plumbing appears to be working and how hydrocarbons in the area are sourced. So if you're not familiar with the San Juan Basin, this is the stratigraphy column of interest. We're going to be spending most of our time talking about the Jurassic and then going into Triassic and even deeper down into things like the Pennsylvanian. I don't think any of the wells I'm going to show you go to basement. The goal is we'll look at a study area map in a few slides, but they want to sequester CO2 within the Jurassic section. Their main target is the Entrada sandstone, and then they're interested in the secondary target of potentially the Bluff and the Salt Wash. What they want to use as seals, or they want to use the Toldilto and the Somerville. So the Toldilto is an anhydrite out here of varying thickness. The Somerville is just a very tight sandstone. Is their primary vertical seal. They want to use the Morrison Brushy Basin member as another primary vertical seal. And then they want to use the Caramel, otherwise known as the Drury Bridge, as their bottom primary seal. Secondary seals of, oh my gosh, it got loose, but wait, we have other stuff before it hits drinking water, include the Mancos, Greenhorn, and Graneros in the top, and then the Chinle, specifically the Owl Creek down here in the bottom. Why they are interested in this part of the San Juan Basin is there is a history of no productive hydrocarbons being found in the Jurassic section. there is a history of successful saltwater disposal into the Jurassic, especially the Entrada. And so that would be a very promising sign for storage. So we're going to be focusing on the plumbing of the system. You know, why are hydrocarbons and other subsurface fluids that we're measuring directly in the cuttings present? How do they move around, and how do these inform our thinking on the movement of injected CO2? Just going a little bit more into the area in terms of what is produced as a resource out here. So in the Cretaceous, there are multiple producing zones, especially the Dakota, although you do have other things shallower that are frequently produced for oil and gas, like the pictured cliffs, for example. There is entrada production, so remember that's what we want to use for storage. There is entrada production in the basin, but that's about 60 to 80 miles southeast of the study area. Remember that because it's going to come up in a bit. In the Paleozoic, especially the Pennsylvanian down here, there are known producing gas and oil zones. Usually those are on the Four Corners platform. In the San Juan Basin, that section typically has gas, but it's usually inert. In the Four Corners platform, Ute and Barker Dome fields, which are what we're going to be talking about, spending some time on today, they do have hydrocarbon-rich sections in the Pennsylvanian. They typically are sour and can contain significant amounts of CO2. A lot of what we're going to be talking about today starts maybe in the Cretaceous, definitely covers the Jurassic, and very frequently goes below the Chinle and often deeper than that. So in terms of where the CarbonSAFE projects have been, just to give us our sense of where in the Four Corners we are, we're over here. The CarbonSAFE project that New Mexico Tech started in 2019 is their phase 3, and that we came in 2021 and started working with them on that Fault project, is up here north of Aztec. They drilled a CarbonSAFE 1 well, as they call it, in 2022. This is a phase 3 project. If you're not familiar with DOE CarbonSAFE nomenclature, phase 3 is where you actually get to start injection, but on a 1 or 2 well scale. And it's just to see how well the injection is actually handled. You do get to make money off of it. You do get to put in for the tax credits. So currently, this area north of Aztec is actually undergoing injection by tall grass. Another phase 3 project began in 25. You can see the 2 planned wells that were going to be drilled as part of that down here, south of Fruitland. That project was halted in October of last year before the planned 2025 wells could be drilled by the Trump administration. In terms of what we're doing and how we can contribute to this, you know, so we have this technology where we can look at rock samples, including legacy cuttings. New Mexico Tech has a great repository out in Socorro, so we went there and got a number of wells, in this case 6 legacy wells. We also got well cuttings from a San Juan Basin operator. We can show the data, we just can't identify the location. They've asked to remain anonymous, so we're going to call that well X when I show you different displays. We also received fresh cuttings and core from the CarbonSAFE 1 well drilled in 2020. Again, the fact that we only need 0.4 cubic centimeters, so first digit of your pinky, makes this analysis very ideal for dealing with repositories where you might only have 5 grams of rock for a given depth. Most of the samples we're going to talk about are legacy. The CarbonSAFE well, obviously those were fresh. There are some nuanced differences between the 2 sample types. We'll discuss that when we get there. So this is where 7 of the 8 wells that we're working on come from. So you can see we've got 3 on the Four Corners platform, and you can see that we've got these 2 down here relatively close to the first CarbonSAFE site north of Aztec. We've got the CarbonSAFE 1 well itself. We've got Kirtland 1 over here drilled in 1961. Down here, we started working on these last year to get ready for those other CarbonSAFE wells that are going to be drilled south of Fruitland. And again, you're working with what are the available rock samples, not necessarily as close as you might like to the study area, but you're trying to work with what you have. Well X is not mapped because of data agreements, but generally I can tell you it's somewhere in this area, okay? Once we started looking at these rocks, once we started understanding how things were structured in the subsurface in terms of fluids and fluid migration, really we ultimately broke the story down into 3 sections. There's this area in the San Juan Basin and its communication or apparent communication with the Four Corners platform. There is, and it especially has a lot of important interplay with the hogback monocline right here. There is this area, which is what was actually used as the CarbonSAFE site. This has kind of an interesting case where there are notable hydrocarbons present, especially in the Jurassic zone. So that's not supposed to be there. But they're also coincident with significant water, so they probably wouldn't ever be a viable resource. And then we have these wells down here in the southern area, and apparent hydrocarbon-like columns across several thousand of vertical feet. They're not viable resource. They're more of a forensic signature, but they're quite interesting. I'm going to definitely try to get through these first two. I'm just going to watch time. I would like to get to number 3. If we don't get to number 3, forgive me. I just want to manage the time well. So starting on number 1, this section here in red, these 4-corner platform wells, really we're looking at things like how do faults affect them. You can see here that we've got these mapped faults in the Cretaceous and in the Paleozoic by Amoco from the 1970s. They identified these on seismic. So these play a big role in terms of how resource is distributed up here, how the Barker Dome and the Ute Dome are plumbed. And then between those faults and the Hogback monocline, they have some pretty appreciable effects going into the basin. So if you're not familiar with the Hogback monocline, this is a map of the surface of the Jurassic in the basin. And this is a pretty abrupt uplift. It's about 3,000 to 7,000 feet, depending upon where you are. It defines the northwest edge of the San Juan Basin. It is not a fault, which is something we actually thought when we started this project, and then we learned it wasn't. There is faulting in the basement and possibly in the up to through the Paleozoic that contributes to the uplift, but it is actually a continuous section, so it's not faulted, it's just really, really displaced above the Paleozoic. In the area that we're looking at somewhere between 3,000 to 4,000 feet of vertical displacement between the basin and the platform. So I said we're going to look at data from legacy cuttings, and I called out Kirtland being from 1961. But a lot of the other wells we're going to look at are from the 70s and 80s as well. So if I'm going to look at cuttings that have been sitting in a drawer, in a box, maybe in a climate-controlled room, maybe not, for literally decades, it's a very fair question. How much can we trust these? How relatable are the volatiles entrained in several decade-old cuttings compared to the subsurface at time of drilling? So this is the volume of liquid hydrocarbons that we saw in Kirtland 1 when we did the analysis of those cuttings across the Jurassic section in 2021. And then about 6 months later, no one knew this was there. Luke Martin dug it up randomly one day when he was working over at the Bureau. It turned out that there was a mud log, including one for butanes, taken on this well in 1961. And if you take a look at where we're seeing these discrete high liquid hydrocarbon responses, and this is the C5 through C10 liquid hydrocarbons, there is an incredibly nice set of feature matches between our data on these legacy cuttings and the mud log from 1961. So yeah, I think we're probably doing a pretty good job of getting information that relates to the subsurface at the time the well was drilled. Most likely what we're seeing are open fractures that effectively are being punched through and giving up that bit of gas, giving that small kick is the wrong word, but that small amount of gas as those open fractures are punched through during drilling, showing up on the mud log. And what we see over here is the hydrocarbon liquids that were also associated with those open fractures. So that data was really encouraging. It shows that we produce meaningful data that can be used to talk about the subsurface at the time these wells were drilled 50, 60, 70 years ago. That is great, because that means that we can learn something that's useful for understanding the area now. It also raised a huge honking question problem. So this little box right here is the study area. This is where eventually we put the CarbonSAFE 1 well. This is Kirtland over here. Here's the issue. This whole area isn't supposed to have any hydrocarbons in the Jurassic. That's why it was picked. And so suddenly you begin to have a little bit of a detective story of why are these here and what do they mean? And it's an important question to ask, right? Are they locally sourced? Maybe we don't need to care. Well, there are hydrocarbons in the Jurassic, especially in the Entrada, and those are produced in the basin. Those are produced about 60 to 80 miles south of the study area, southeast of the study area, and they're thought to be Toldelto sourced. Gonna have to break the flow here and take people back to organic chemistry. Forgive me if you're just kind of dreading this moment. I'm gonna use some nomenclature here. When I talk about paraffins, I'm talking about alkanes like this guy, hexane. When I talk about naphthenes, I'm talking about cycloalkanes like this guy, methylcyclopentane. They can also be 6-membered rings. I think most people understand what aromatics are. These are in this case, these are 6-membered rings that are conjugated. That means essentially that they don't bend, that they're very rigid, flat structures. The other thing to know is that as you go in this direction, you become increasingly volatile, increasingly soluble in gas. That decreases with the greater number of carbon atoms in the molecule, and that solubility with gas increases with branching. Why I walked you through this will matter in a second, I promise. So coming back to Kirtland 1, here's the data that we see on Kirtland 1. We have these discrete high liquid hydrocarbon responses here in green. This gold track is looking at the percent composition of aromatics. And you can see that when we get one of these high liquid hydrocarbon responses, which is probably a fracture, the aromatics take a dive, right? So that's nice. This lets us identify something that actually looks like resource based on the aromatic composition and the presence of it physically being there based on the high liquid hydrocarbon response. You can do fun things like cross-plotting this to decide what is real resource that you want to investigate and interrogate compositionally. We ended up picking these 24 depths based off of this cross-plot, is saying that these were open fractures that actually had hydrocarbon resource in them, or something that looked like real hydrocarbon resource that you might produce. And we carried that forward. We wanted to see compositionally what those fractures looked like. So here's what we find. There's actually 3 different populations based off of, in this case, a compositional parameter of just paraffins over paraffins plus naphthenes that are statistically significant in terms of these being grouped as their own populations, that they are meaningfully different from any of the other populations. Okay, we know that we have 3 different populations of liquid hydrocarbons. Well, that would suggest at least 3 different charging events, whether it's the same source rock or a different source rock. You could open that question up. I will say that this distribution of going towards higher and higher paraffin-naphthene ratios is consistent with thermal maturation. So this could be the same source rock pulsing in charge through these fractures at 3 different cases of maturity. What matters to us is that as we start looking at how these fractures are distributed, here they're color-coded by those 3 different populations. But if we take a look at where they're organized in terms of depth, what formation they're in, here's the key thing. They don't care about what formation they're in terms of how they're organized. They don't care about vertical seals. They appear to be discrete, and all of this suggests that we're looking at fractures that were laterally charged and do not care about any of the vertical seals in the area. So again, there's a big case to be made that this is probably looking at, increasingly thermal mature charge for maybe the same source rock. But what I really want to focus on is this question down here. So we have these 3 different populations of liquids in the hydrocarbon liquids in the fractures, and it suggests that the fractures of the Jurassic section of Kirtland 1 were charged with 3 different sets of hydrocarbon liquids of different maturity. So that might represent 3 different pulses from the same source rock at different stages of maturity. Why am I still going through this, and why am I still talking about this? Okay, here's the thing. This just turned into something that looks much more like a conventional oil migration story. And this isn't oil. This is condensate being carried with a gas. But now we have direct evidence that we have pulsed condensate resource into the Jurassic section out here, and we've done it multiple times. So that means that we have lateral fractures that can serve as active migration conduits, that have a demonstrated history of serving as active migration conduits, and based on the mudlog data, were to a good extent open in 1961 when the well was drilled. So you start thinking about what does that mean in terms of migration. There are different chemical compositions that we can use to look at gas migration. We like to use the ratio of this guy over here, toluene, versus all heptanes. We don't normally break out in heptane versus different isomers of heptane. The value of that is there was some great work done by Keith Thompson in the 80s where he used the ratio of toluene to N-heptane to look at gas migration. If the value went very, very high, that would suggest that you'd moved gas through and you had stripped the light volatiles that could carry it in that gas as a condensate from the system. If the value went very, very low, it suggested that you had entrapment of a migrating condensate that was being carried by a gas. You know, he was able to demonstrate these values in the field in places like Alaska and the Williston Basin, and he was even able to repeat some of these mechanisms in the lab. So for example, this is a very small data set right here. I just want you to pay attention to the y-axis. In this case, he starts with this circle, that's his oil. He flows gas through it. This square represents, and this is increasing toluene over heptane. This square represents the new composition, so it became more toluene enriched of that residual oil. And this asterisk down here is what is in the condensate gas that he flowed through that oil. He started off as dry methane. And you can see it pushes the value lower, right? Because it carries more heptane that is gas soluble and leaves behind the toluene. Single data point, not the best one. He did a lot more experiments to build this out. But the point is that we're wanting to use the signature to look for evidence of moving gas through or in placing resource. So if we take a look at the salmon line, and this is on a log scale, you're looking for orders of magnitude difference with the signature. We're using all heptanes because, again, we don't normally break out the isomers. You can see that on this log scale, we go significantly low where we have these high liquid hydrocarbon responses, right? And so that tells us that these fractures were charged by gas migrating through carrying condensate. Okay. That also means that somewhere nearby is the end of that pathway, right? But somewhat concerningly, you can see there's also depths, again, remember log scale, that have very, very high responses, and there's not really any significant hydrocarbon associated with them. And so we don't have to just worry about these lateral fractures that were charged with condensate. We probably also have to worry about lateral fractures where the migrating gas kept moving. It didn't stop at Kirtland. It kept moving probably further into the basin. And so, again, you're building the story of, okay, we found these unexpected hydrocarbons. We realize they represent multiple cycles of charging. Are they all from the same source rock or not? Open question. But now we know there are migration along these fractures. That migration is probably lateral. And we also know that that migration potentially progresses further into the basin than what we would suspect if we just took Kirtland and used that as our measuring stick. So the question really becomes, where are these hydrocarbons from? They're not distributed in a way that could be sourced from the Toldoto. And so you start looking around. So we had these other wells on the Four Corners platform. This is Stevenson number 1. It's the closest on the Four Corners platform to the San Juan Basin. We've got a really huge section here. You can see about 7,000 continuous feet of cuttings that we've analyzed. We're starting off, I believe this is in the Dakota. No, this is in the Lower Mancos. And we're going all the way down into the molasse, so well into the Pennsylvanian. Now down here is the known pay zone. There are pay zones on the Four Corners platform down here in the Pennsylvanian section. And this is the composition of the hydrocarbons that we see. And this is a very, light compositional description. We're just looking at pentanes in red versus decanes in black. But what we see is that when we look at the composition over here in those fractures, and again, this is a very simple comparison. There was more work done than what I'm suggesting here. It looks like a very similar resource. Now, I've aligned these on the same TVD depth scale. Remember, there is displacement across the platform. And so, yeah, you start to have a world where, okay, there are pretty big faults on the platform. Some of those faults are right next to the hogback monocline. There's probably significant fracturing coming off the hogback monocline. And you start thinking that the way that we probably got this resource here is we probably went across the hogback monocline and then moved laterally across fractures. So this starts to really present an interesting story, not just in terms of, hey, wow, isn't this fascinating in terms of the plumbing? It's a little bit of a, hey, wow, if hydrocarbons moved along these pathways, could injected CO2 move backwards along these pathways? Now, granted, there's a lot of questions about what is the time scale that that's going to happen on, but if you're at the very early stages of a project and you have the room to make conservative choices about risk, you want to go with those conservative choices. I will say that compositionally, because we can calculate what we think we can calculate the API gravity of the resource in those fractures, the most mature charge does look very similar to the gravity of the produced liquids on the hogback monocline in some parts of the Pennsylvanian. So another little piece of, another little tidbit that would suggest this is the mechanism for how we got this resource and these fractures that don't care about vertical distribution into this part of the Jurassic. So if we come on to the Four Corners platform itself, the questions get even more kind of bizarre and more concerning. So production out here is mostly dry to wet gas. That means that we're going to probably be paraffin dominated. Those are the things that can be most volatilized, be carried in the gas, and we're probably going to see aromatics as the minimal species. Kirtland over here really matches that story. This is the C8 liquid hydrocarbons, so octanes, stuff like ethyl cyclohexane for the naphthenes, C8 aromatics, so things like ethyl benzene or xylenes. And we can see, and again, log scale, we're dominated by the octanes. That's exactly what we should see out here, what we would expect based off of gas composition. Over here on the Four Corners platform, it's the opposite story. We are being dominated by the aromatics. The least gas-soluble compound is dominating the hydrocarbon composition over here. What is going on? How do you achieve that, especially when you know that compositionally you should be looking for something that's going to be dominated, in this case by octanes, the way I'm displaying the data. One of the ways you get this, remember we're looking at the rocks, not necessarily the produced fluids, is if you move, again, massive and massive amounts of gas, like we talked about in a lateral configuration, you will leave behind aromatics preferentially because those don't travel with the gas. Well, guess what? It turns out that Stevenson sits right on top of a fault that goes all the way from the Pennsylvanian to the Cretaceous Dakota and might even express at surface. And what this would suggest is that we've had across this 7,000 feet of section we're looking here on this fault, massive vertical upwards migration of gas. And that has taken these lighter, more gas-soluble compounds along for the ride and left us with an overabundance of aromatics. So this is a very nice piece of work. It's a field guide with the Four Corners Geological Society. It was put together by the Amico geologist that was in charge of Ute Dome in the 60s and 70s, I believe. They ran a number of seismic studies out here. No, the Four Corners Geological Society doesn't have that seismic, but you can see the faults that they identified being mapped out here. Here is the Pennsylvanian, here is the Cretaceous. And a number of these faults actually, probably cut all the way from the Pennsylvanian to the Cretaceous. And so I've gone ahead and I've color-coded our wells. This is Stevenson, the one I was just talking about that has all these migration signatures. This is Gotor over here. It has a similar case. Over here, we have Ute 8 actually in Barker Dome. And you start to get this interesting story. If we use that gas migration signature, pseudo B again, this is the comparison of all three wells, including Kirtland on a log scale, right? And again, low values, orders of magnitude low values would indicate emplacement of condensate. High values, order of magnitude higher values would indicate we've migrated gas through. And this wasn't done on purpose, it was just serendipity, but you can see that Gotor and Stevenson do sit right on top of these deep faults. And so what's happening is that we're looking at the migration of Pennsylvanian gas all the way up section that we're measuring on both of these wells. Conversely, when you take a look at the composition in the field of what you have in Barker Dome versus Ute Dome, something weird happens. If you take a look, for example, at the gravity of the liquids over in Barker Dome in the Cretaceous Dakota, it's very light, almost 90, right? In the Cretaceous Dakota over in Ute Dome, it's relatively heavy for a condensate, 40. If you take a look at the GOR, 87 MCF per barrel, what's happening over here at Barker? 34 MCF per barrel and even higher gravity liquids. That really starts to be a little bit odd. And you take a look at this plumbing, and we've already discussed how we probably have vertical migration up on both of these wells from from the gas zone in the Pennsylvanian up through the Cretaceous. But you come and you look at this one over here in Barker, and I know it's all saying Ute Dome Field, but trust me, this is the extension out into Barker. And you actually start seeing, hang on, skipped ahead here. You see the pseudo-B, that gas migration signature, actually pulls very low in both of the known gas zones, in the Pennsylvanian gas zone and in the Cretaceous gas zone that's produced in Ute Dome. And if you take a look at the plumbing, this starts to suggest, okay, we have massive vertical migration up, and then on top of it, this is the upper fault block. We're dumping some of that migrating light condensate probably over here into the sands that are available as reservoir on the Barker Dome side. And that also potentially gets at explaining why are these production numbers in terms of the gravity, but still higher gravity but lower GOR, so different over here in Barker up here as opposed to down here in Ute Dome. So I hope I'm doing something of justice to trying to explain this, but you know, you really start getting this sense that, okay, the plumbing's coming together. We have vertical movement up these deep faults. Some of that uses faults like this one right here, which actually defines the southeastern extension of Barker Dome to dump that migrating condensate that's been stripped into places like Barker Dome. That's why we have lower GOR but higher gravity liquids. And it's fascinating to kind of think about how all this moves around. There's other things that you start seeing too. If you take a look at the CO2 across these 4 wells, you know, you can kind of guess, okay, again, log scale. We've got some kind of baseline sitting out, you know, between 400 to 500 nanomoles of CO2, maybe 300 to 500 nanomoles of CO2. But you see other things too. For example, this one, Stevenson, which is this guy right here, right on the edge, coming right up to the hogback monocline, has a whole order of magnitude more CO2 in it. Now, the Pennsylvanian gas out here is very CO2 rich. It's like 22 some odd percent, 21%. So you can imagine that if you were to start migrating not just gas, not just hydrocarbons, but some of the other things carried, you might start migrating large amounts of CO2. So we think that's why there's so much CO2 here. You can push that story a little further by looking at, I'm gonna hop ahead for a second, by looking at things like how the CO2 is distributed in relation to these gas migration signatures. So this is Stevenson, the well we were talking about in gray that had the 10 times higher CO2. And I'm just showing you the Jurassic section here because something really fascinating happened. If you assume that CO2 is migrating up this deep fault along with all these other gases that are showing up in the migration signature, then, you know, does it just go up out the top? What happens to it? So when we hit the Jurassic section, and that's all that we're looking at here, I've color-coded this. Gold are the secondary sealing features, red are the primary sealing features, blue is what they want to use as reservoir. And what you see is something really fascinating where if we assume that CO2 is migrating up from below, look at this, look at where the CO2 is accumulating. It's accumulating in the target reservoirs, and every time it hits one of these major sealing features, for example here at the Brushy Basin and salt wash contact, it takes a step down. So we actually get to see that this migrating CO2, this is a huge risk. You wouldn't want to inject anywhere on the Four Corners platform near this guy. But this is also showing that this model that New Mexico Tech has, that some of these sealing rocks they want to count on, that, you know, they actually work. This is the gas migration signature. It goes very low. So we're depositing this migrating gas here in the entrada. And look, this is the highest CO2 in this whole wellbore. And look at how it falls away. As we go into the Toldilto and the Somerville, we take a step down. As we come through some of these other interfaces, like the Brushy Basin versus salt wash contact, we take another step down. So we can actually see that, yeah, there has been an instance of CO2 probably migrating on one of these deep faults. We can also see that, you know, there's an interesting qualitative piece of information speaking to the strength of New Mexico Tech's model in terms of what's going to stop CO2, what's going to vertically impede its migration. So that's wonderful in terms of providing some evidence that these seals work in a natural experiment. It also, unfortunately, gives us a pretty strong piece of evidence that, yeah, these deep faults on the Four Corners platform can likely migrate CO2. And so what you take away from this area, that red circle that we were looking at when I started talking about these 4 wells, is that we have a rather complicated system where there's evidence that we have lateral fractures extending out from the hogback monocline into the basin. Those have evidence of being charged by Paleozoic Pennsylvanian gas that is present on the Four Corners platform. We also have evidence that some of these big faults on the Four Corners platform can vertically move quite a bit of gas, including CO2. And so then the concern becomes, okay, what happens once we start injecting CO2 in the San Juan Basin? Could it get on any of these lateral fractures and start using them as migration conduits? If it makes it back to the monocline, what's going to happen? Well, there are these deep faults that have a history of migrating gas, including CO2. And so that all becomes a very concerning risk scenario. Now, the nice thing about it is that where the CarbonSAFE well was placed is far enough away that we're not really encountering any of these kind of lateral fractures, but it does tell you that you want to be careful about how close to the hogback monocline you come. So just for the sake of time, there was a little bit more in that section, but I'm gonna skip through that because I want to talk about this blue area here, and then time permitting, we'll get onto the green area. So the other area, which became arguably more important because this is where the CarbonSAFE well was actually drilled, and this is where injection is carrying on right now, is this area north of Aztec. So only one well is shown, but this other well from the operator, Well X, is somewhere in here. I will tell you it's relatively near the hogback monocline, and it's near one of these Jurassic faults that you're seeing over here, but it doesn't sit on top of the Jurassic fault like what we have over on the Four Corners platform. Why this area got interesting is, again, we encountered large quantities of hydrocarbons that weren't supposed to be there. Now, those were present with significant amounts of water, so it wasn't an economic resource, but you get to do this whole detective game again of where did these hydrocarbons come from, because we just were busy arguing that, okay, we need to write off this area for CCS activities because we have evidence of lateral migration along open fractures that could move back to the hogback monocline and then move up one of these faults to get into at least the Cretaceous. So this is Well X. These are legacy cuttings that operator provided us. Again, this one wasn't mapped, but this is a very similar display to what I showed over here with Kirtland. So this is the display from Kirtland, liquid hydrocarbon responses versus aromatic content of those hydrocarbons. Take a look at the scales. The hydrocarbon response is 0 to 30 ppm rock volume here. The hydrocarbon response on this one, forgive me for flipping axes like that, this maximum response is 600 ppm hydrocarbons. We see this whole slug here that starts in the brush, kind of in the middle of the brushy basin and comes all the way down to within the Somerville, approaching the Toldilto. And this is a continuous thing. It's not discrete responses like what we had in the case of the fractures. And it's a very significant response too. It's over 100 ppm of the volume of liquid hydrocarbons in terms of the volume of the rock that we're measuring. All right. So remember, this area was picked because there weren't supposed to be hydrocarbons here. And now there's 10 times greater quantities than the fractures that we saw in Kirtland. So again, you get to do this whole little detective story of how did these get here and what does this mean? Now, the composition does suggest this is potentially not a viable resource. These are relatively aromatic rich compared to what you would see. Most oils are going to be around 10%. They might go higher, so you could argue this is an edge case. And most condensate is going to be significantly lower than 10% because the aromatics aren't gas soluble. But these hydrocarbons are still here. They aren't supposed to be here. And they have a very different distribution than what we saw at Kirtland. So again, we measure water as one of the other volatiles that we look at, and we know when we make these measurements of water, they actually relate pretty well to the volume of water on the subsurface. So take a look at the distribution of water, right? So I don't think you would ever want to try to produce this resource. I can't tell you what the water cut would be, but it's going to be high. So it's not a viable resource, so we can at least stop worrying about that. We're not killing someone's resource. We can also see that there's probably pretty significant degradation of that resource going on from biological responses. This is formic acid. Under these temperature conditions, you're probably making this by microbial action. This is the ratio of paraffins to paraffins plus naphthenes. Paraffins are a favored feedstock of most microbes in the subsurface. You can see when the organic acids go high, we get discrete pullbacks on this ratio of paraffin to paraffins plus naphthenes. So this resource is in a pretty significant water phase. So whether it's residual, whether it's its own phase, there's a lot of water nearby, and it's being very actively degraded. It's not going to be good quality. Great, we don't need to go argue about are we killing a productive zone. We do need to address this question of where did these hydrocarbon liquids come from, because it was a real issue with the case over in Kirtland. So eventually we drilled the CarbonSAFE 1 well. That had a lot of significant hydrocarbon shows in it as well, although those were present in sections that were very, very water dominated, potentially undergoing significant biological degradation. So pretty similar story to well X. Now the nice thing is that we had this core from CarbonSAFE, and I don't know if people can see this well, but we got a few feet of the Toldilto before we went into the reservoir section in the entrada. And what we actually see is the Toldilto, instead of being a nice clean anhydrite, is actually a very organic rich rock, and we see quite a bit of oil staining going into the entrada. So this tells us something pretty important, that yeah, we've got very meaningful hydrocarbon responses across the Jurassic here. Now the nice thing is that right here, this is where the brushy basin starts, and that's one of our primary seals. And you can see the hydrocarbons just fall away. There's other things that change there too. So for example, this is helium. Helium undergoes a stepwise change at the interface of the Dakota and the brushy. That would be another indicator of a good seal when you go from high helium to low helium. If you can vertically impede the movement of helium, it's a good evidence of seal. There are changes in the distribution of CO2 that would again suggest different chemical compartments. So we don't necessarily have an issue where, you know, our seal, our topmost primary seal in the brushy basin isn't working. It's halting these things, but we still have hydrocarbons up and down the section. The nice thing is that at least we have a reasonable explanation for it that doesn't involve long-scale migration that could be an issue. These are all probably being locally sourced from this organic rich Toldilto that we catch a little bit of here in the core. So let's see. I'm just trying to be mindful of time. We'll go back. We'll hit this too. So the other thing that we see that does give us a little bit of concern is that there was an image log taken on the well. The way this is displayed is not doing it great justice, but each of these thin lines is a fracture on the image log. And you can also see that a lot of these discrete oil and gas responses, hydrocarbon liquids in green, hydrocarbon gases in red, correlate quite nicely to the presence of those fractures. So, you know, we have resource sitting in open fractures. Again, we have the evidence of a good vertical seal. We have a story where we can argue about local generation here. But this does cause some questions about, you know, how much lateral movement might there be out here. We do see a few oil migration signatures in this section. So for example, this blue track right here is the ratio of toluene to benzene. We use that as an oil migrating signature. If you look at the composition of produced crudes around the world, the ratio is usually 3. Sometimes gets above 5. So if you start seeing values, especially in excess of 5, then that's probably an indicator that you have lateral migration. And the way this is scaled, or you have migration, the way this is scaled is not doing us justice, but again, there are local highs on these fractures that are identified in the image log. So it's a somewhat interesting story. We know that the vertical seal, at least in the brushy basin, is working. We know there's a lot of hydrocarbons, but now we have a reasonable story for why those hydrocarbons are there. They're locally sourced from the Toldilto. We do see there is some evidence of still lateral movement, but it's not this large-scale lateral movement across the hogback monocline that we were worried about over at Kirtland. I'm going to skip through a little bit of this just for the sake of time. So that, let's see. So for us, that's both a blessing and a curse. Like, it's nice. We can now understand where the hydrocarbons came from in well X. They're probably Toldilto sourced the same way they are here in CarbonSAFE 1. So we don't have long-scale migration, but we are going to still have these concerns about how much migration potentially can happen on these open fractures. Other positive take-homes from this, though, are that there is pretty good evidence of meaningful vertical seals. So, it's somewhat of a mixed bag. They're definitely going to have to watch how the plume expands. The plume might start to expand running along these open fractures that have some evidence of being used as migration conduits for the locally sourced hydrocarbons. But at least we're not developing some kind of story where, again, we're looking at migration over tens of miles from the hogback monocline that then involves access to vertical faults that could allow us to just, again, no one really has a good sense of how rapidly injected CO2 would move along those lateral fractures, but the scenario is it moves along them, hits the hogback monocline, hits a fault, goes up. That really doesn't look like the case we're encountering here, but again, they are going to have to probably watch how the plume expands, because it's probably going to expand in a relatively non-ideal way, potentially. I want to really emphasize the word potentially here, along some of these open fractures that have evidence of oil migration on them. Okay. So this brings us to the southern section. I know that we're past 7:30 right now. So we can try to discuss the southern section. I'm happy to go into it. Or we can just kind of open the floor for 10 to 15 minutes of questions. I am sorry that I'm not just plugging away at this, but I want to be respectful of people's time. I know this is a very dense topic, so I want to give folks the opportunity to ask questions. One of the other issues that I get into is I sit there and I speak with a lot of petroleum geologists all day, every day, and I'm very aware this is a hard rock mining state, so questions might be a good idea if we're going to talk about fluid flow in the subsurface. So I'll just open up to you guys. We can talk about the southern area, or we can just kind of go to questions and talk about these two areas in the north that I spent the last hour speaking to. Yeah?
So when you form hydrocarbon deposits, you have oil, gas, and water.
Mm-hmm.
Maybe you can comment a little bit more on the water, this thing.
Mm-hmm.
The question is, if that water moves the same time with the hydrocarbons or a little bit later?
Do you mind repeating the question?
So I just repeat, when you form hydrocarbon deposits, typically what you see in the traps is water, oil, and gas. And we talked a lot about the volatile, the hydrocarbons and the gas, but I'm interested in the water and what role it plays in all this.
Yeah. So how the water moves around is a great question. We use those gas and oil migration signatures because they work based on ratios of hydrocarbons that are preferentially left behind, get fractionated, left behind in the rock during those processes. We don't have any similar indicators for water, so we don't really try to comment on how water may or may not be moving. There are water-soluble compounds that we do directly measure, so not here. There have been studies where we will try to figure out, is the water compartmentalized based on what's dissolved in one area versus the other. That wasn't a terribly fruitful thing to engage in here. What I will say is that, bizarrely enough, looking at things that are dissolved in the water, on the CarbonSAFE well, we can hop over to this data if you want. I didn't show it here. Looking at things that are dissolved in the water in the Jurassic section actually even further makes the argument that the Jurassic section is vertically isolated from what's above and below it that they're counting on, so that things like the Brushy Basin and things like the Dewey Bridge caramel on the bottom are doing a good job of isolating the zone they want to do injection vertically based on those things that are dissolved in the water. But no, in terms of looking at the actual migration of water, we've thought about doing water isotopes, but we haven't pulled the trigger on doing that. So there's not a lot we can say beyond kind of looking for those compartmentalization signatures.
And another question on the lateral movement. Can you give us an order of magnitude? Is it tens of miles or 100 miles or?
Yeah, so here, let's go back to the very first map. Oop, I don't think it liked that. All right, so looking at this guy. So here's your I don't know why we made the map like this. This scale bar is 9.5 miles, okay? So you are talking about something on the scale of a little less than 10 miles between the Hogback monocline and Kirtland 1. So those fractures that were charged with condensate, at a minimum, you could say that that's kind of your length of concern, something on the scale of 6 to 7 miles. Now, potentially the scarier thing is that when you calculate the API gravity of the hydrocarbon resource in those fractures, and we're pretty good at this. We usually get the answer right within about 2 degrees of what the real answer ends up being when we compare our calculations to tests. That resource, in terms of the API gravity, actually looks like the oil resource in the Pennsylvanian over here in Hogback Field. All right? And so there are similarities in the composition of the liquid hydrocarbons between Stevenson 1 in the Paleozoic Pennsylvanian section and what we're seeing in the Jurassic section of Kirtland. So we feel comfortable saying that those resources were probably sourced from the Pennsylvanian. The issue is that you can't really do a true genetic analysis of what you have over here versus what you have over here. The gas migration signature, changes stuff enough that you can't sit there and use, some kind of regressor to get, an apples to apples answer. But if you take that idea of the calculated gravity in the most mature set of charges that we see in the fracture, and you say, okay, where do I have resource that has the same gravity as that? It's over here in the Pennsylvanian section of Hogback Field. And so then the question becomes, is this the pathway that matters? Or do you actually have an argument that this is the pathway, right? So at a minimum, you want to start thinking about stepping off somewhere between 6 to 7 miles from the Hogback monocline. I didn't do justice to this, but our suspicion is that these deep faults really probably play a major role in that too. It's not just having the Hogback monocline present. So at a minimum, you want to be stepping off probably 6 to 7 miles, but there's a case to be made, that might be the better part of 15 miles maybe. So you could make that argument that maybe you need to be stepping off even further. What I will say is that over here at CarbonSAFE 1, across the entire section of well, we only saw one fracture, just literally one. It was a single data point that you could maybe say was this case. And it would be a real stretch to say for sure that it was. So we don't think that we're seeing any of the kind of fractures that we see at Kirtland over here at CarbonSAFE 1.
Thank you.
Can you hear me? Okay. I was wondering if you can measure biomarkers, because that would help you with the source to oil correlation.
So if we can measure
The biomarkers in
the biomarkers, no, not really. So it's just the C1 through C10 hydrocarbons. So we can look for compositional similarities across that range. You need to be careful because it's easy to start shifting them if you've had a lot of gas migration. That can just drag those signatures to where the really light stuff like pentanes, hexanes, and heptanes is preferentially diminished, right? So that's why I was kind of speaking about doing any genetic analysis is a somewhat fraught process. You can say that there is a pretty strong set of similarities between the Pennsylvanian Paleozoic and what we see in the Jurassic section of Kirtland 1, but I don't think the quality of the data, just because of the nature of what's happened at Stevenson 1, at GOTOR, the wells on the platform, is such that you could try to do a genetic comparison of the composition of the resource.
This is a less technical question, but so if I understand the process of the CarbonSAFE 1, if you've got horizontal fractures, but your seals look like they're pretty intact, so that makes it a reasonable target. So if someone were to start injecting CO2 in the subsurface, how is that monitored? I mean, how do you monitor what's going on with the CO2?
Yeah, so the standard requirement is that you have some kind of seismic monitoring to watch the growth of the plume. I don't know what Tallgrass is specifically doing. If they're going out there and getting a new 3D seismic every year, or if they have kind of offensive monitoring stations that collect one-dimensional data, that's another approach that a lot of people are looking at too. So I don't know which one they're doing, but they are using seismic approaches to monitor the growth of the plume. They are injecting there. They've been injecting there for over a year now. So I don't think they have any. I think the data on our data, all the great work that was done by everyone else on the team, didn't flag any huge issues, didn't flag any major points of concern with the vertical system. My only concern would be, they need to monitor the plume, because the plume might start to grow in somewhat non-ideal ways if it starts traveling preferentially down some of these open fractures.
Hi, you showed a couple wells. One, there was like a correlation with the CO2 and the hydrocarbons they were sort of tracking, and then there was one where they weren't. And then the X well, you showed a CO2 and hydrocarbons or CO2 and formic acid, where you had spikes on both of those?
So this is the X well. Green is liquid hydrocarbons, C5 to 10. Blue is water. It's a direct measurement of water. Yellow is formic acid, and this somewhat different blue is the compositional ratio of paraffins, so alkanes versus cycloalkanes, naphthenes. The point that I wanted to make here is just that this resource is chock full of water, so it's not really a viable resource, and it's pretty actively undergoing degradation. Were you talking about that, or were you talking about
that was
this
one
display?
of the, where you got the spike on formic and CO2.
Yep.
Indicating bacterial.
Probably locally sourced CO2.
Well, that was the crux of my question is, what do you think the origin of the CO2 is? Is it biogenic, or is it thermal, or is it
let's just show this.
diagenetic?
I think I've got the slide in here at the end. All right. So this is the core, not the cuttings. This is the core. This is unpreserved core, so it's not the most response that you could get. And so this is mostly looking at the Jurassic section. The cuttings display had a much larger section, right? So here we have liquid hydrocarbons. They're relatively low. We come down here into, what is that? The entrada, and you can see that it neatly picks up, right? And you have different controls when you look at unpreserved samples versus preserved and fresh samples, which is what those cuttings were. But you can see that it does a nice job of kind of showing, okay, we have charge throughout the entrada here. It's not a lot the way this is displayed, but it's notable. This is CO2 on a log scale. And where this gets very interesting for us is, remember, the baseline at Kirtland in the Four Corners platform was somewhere around 5 to 300, okay? Stevenson, which was kind of our one-off high CO2 response, was maybe 2 to 5,000. This guy, this guy is like around 50,000. It is chock full of local CO2, and this is a biological signature. This maroon track, this is methyl ethyl ketone, so it's different from the organic acids. It has a preference for the oil phase, so if it's generated by the degradation of oil, it will stay put where it's generated. And take a look at this. Where we enter the entrada, which is where this resource is showing in the core, this is, again, that compositional signature of alkanes versus cycloalkanes. And again, remember, the bugs like to go after the alkanes, the paraffins. It just steps down, and the methyl ethyl ketone signature just steps up. And then you get past it, and when you're into the sealing features and the Dewey Bridge and the Chen Li, it steps down again, the oil steps down again, and this ratio steps back up, right? So the entrada is chock full of water, and that water is probably chock full of bugs, and it has so much native CO2. It's very impressive compared to all the other wells we looked in the study. We actually thought we had done something wrong, and I insisted to my boss over and over again that we go back and look at the data, and he's like, no, there's just that much CO2 there. So yeah, there's probably a lot of local biological action generating quite a bit of CO2 in the entrada here.
Do you see any H2S?
So we can actually measure H2S. We don't see it significantly here. There were 1 or 2 depths where it went off. Well X and the larger cuttings section from CarbonSAFE, where it's the fresh cuttings, not this section of core that I'm looking at, they have meaningful H2S responses in the Mancos up. That is not new. That's been documented in the San Juan Basin. There is every chance that that H2S was either already there or it might be due to field activities. Where CarbonSAFE 1 is drilled, there are 3 offsetting wells that produce something like a TCF of gas from the Mancos, Dakota, and elsewhere in the shallower section over the course of about 30 years as conventional completions.
But you had a graph where H2, in one of the charts, H2S correlated the CO2 in sour gas, and there was high CO2 as well. So that seemed to correlate.
So the Four Corners platform, so not the San Juan Basin, the Four Corners platform on Ute Dome has, you're right, has 2% H2S, I believe 21% CO2 in the gas composition. Yes. Yeah. So actually that's an interesting story too, and I skipped this for time, but we don't just see evidence of CO2 moving up section on those faults, we see evidence that the sulfides have moved up section. And the sulfides have actually changed the surface chemistry of the rock to where the way the rock interacts with CO2 on the platform is radically different from the way the rock interacts with CO2 in the basin.
Do you see, when you have these red rocks on the Colorado Plateau, you see these white bleached zones on faults that go up, and that's the H2S that's bleaching the iron, the ferric iron, and that's why the hematite goes away.
Not sure. I think maybe you and I chat about that a little bit more if you want, either tonight or I'm in town the next 2 days.
Let's thank Christopher again.
Again, thank you all for sticking with this. I know it's a ton of stuff, and I realized about halfway through that the narrative probably needed some tuning for a hard rock audience. So again, thank you for sticking with me, and if you found it interesting, happy to chat with you more.